Hi, I'm Tom Dick. I'm a math professor and a math advisor for Texas Instruments. This short video is part of the TI-Focus AP Calculus series. We're going to take a look at using the TI-84 to investigate a problem involving a function whose derivative is presented to us defined in a piecewise way. To start off with, let's just talk about how you can enter a piecewise function on the TI-84. I've gone to the y equals menu, and you can see I've already got such a function entered for y1. I'm going to use y2 as just a way to demonstrate how we do this. So I've gone to the math menu, and if you go all the way past the bottom to B, you'll see piecewise. That gives you an option of defining how many pieces you would like in your formula. It can be anywhere from 1 to 5. To illustrate, let's just do a formula that's in 2 pieces. So I've selected 2, and notice that y2 now has presented this template where I have spaces for 2 formulas as well as the specific domains for x values that those formulas will be valid for. Now for my first formula, or first piece, I'm going to enter x plus 2, and I'm going to state that this will be valid for the values of x that are less than or equal to -1. To get the less than or equal symbol, I go to the test menu, get the 6th one there, and then I'll enter -1. And now I'm ready to enter the second formula piece. So I go down to the second formula, and let's make this formula equal to, let's say 3 minus 2x. And once I've got that formula, we'll need to enter the values for x for which that formula will hold, and that'll be the values of x that are greater than -1. So I'll go back to the test menu, pick up the greater than symbol, we'll enter -1, and that's going to complete our definition of this piecewise defined function for y2. Let's take a look at the graph. You can see that the graph's in 2 distinct pieces. Both are linear, and that corresponds to the 2 formulas that we entered. There is a discontinuity in this function where the formulas switch at x equal -1. Now I've gone back to y equals, I'll clear out y2, and let's turn our attention to y1. This is the function that was presented on the Common Exam questions AB3, BC3 in 2018. This function is equal to -3 for -5 less than or equal to x less than -2, 3x plus 3 for -2 less than or equal to x less than -1, and this next piece, absolute value of x plus x, that's actually going to end up being equal to 0 for x between -1 and 0, and 2x for 0 less than x less than 1. The next piece is just the constant 2 for 1 less than or equal to x less than 3, and the very last piece is 2 times the quantity x minus 4 squared for 3 less than or equal to x less than or equal to 6. Now, this function was actually displayed graphically on the exam, so I'm going to go to the window and make my settings match those of the graph that was displayed on the exam. X-min will be -5, X-max 6, Y-min -3, and Y-max 8. And now if we graph this, we'll get a display on our TI-84 that's very much like the graph that was displayed on the exam. Now I'd like to touch on what I think is a point of confusion sometimes for students. Notice this graph has several sharp corners in it. These places where the graph changes direction suddenly are going to be points of non-differentiability. But that's for this graph. This graph could be the derivative of some other function. And in fact, that's the function we're going to be interested in investigating. Let's create the function. The fundamental theorem will give us a recipe for doing this. So I'm going to go back to y equals to y2, and I'm going to create a definite integral function. So I find fn_int from my math menu, and we're told that we want a function that has y1 as derivative and the value 3 at x equal 1. So that's where I'm going to start measuring my definite integral from. Lower limit of 1, integrate up to x, our independent variable. We'll integrate our y1 function. Let's integrate with respect to t dt. And this definite integral function is guaranteed to have y1 as a derivative. But its value would be 0 at x equal 1. So if we want to get a value of 3, let's just add on 3. And now we have a function that has y1 as a derivative and has the value 3 at x equal 1. Let's take a look at the graph of this. Now, this is a very computationally heavy function for the TI-84 to work with. So what we're going to do is go to the window and set the x-res from 1 to 3. So it's actually going to calculate only every third pixel across the page. Keep in mind that what it's computing when it's computing y2 is for every point it computes, it's computing a complicated definite integral. Here we can see the graph is coming up fairly slowly. That's because it's having to do so much computation to get each point. But here we go. And so this red graph is a graph of a function that has y1 as its derivative. And we're almost done here. And that should just about do it. Now notice that this function is actually quite smooth. There are no sharp corners in it. And there couldn't be because it has a derivative, namely the function given in y1. All right. Now where y1 is equal to 0, our graph will have to be perfectly horizontal. Where y1 has a constant value -3, our graph has a constant slope of -3. And when our graph has a constant value of 2, our antiderivative has a constant slope of 2. What else can we see? Here's where the derivative is increasing. That corresponds to our graph being concave up. Here's another spot where it's concave up. Again, that's where the derivative is increasing. And in fact, it's both, our function is both increasing and concave up there. Over here is an inflection point. And that's because our derivative changes from decreasing to increasing there. So these properties of our graph correspond exactly in the right way to our derivative graph. Now I've turned on the trace, switched over to our antiderivative function, and just double checked here at x equal 1, we had the y value of 3. We can trace along our antiderivative graph. One of the questions in this problem was, what's the value of the definite integral of our y1 between 1 and 6? So I'm going to go ahead and jump the trace over to 6, but remember that we added 3 onto our definite integral. So the definite integral from 1 to 6 must be about 10, and that's why we're getting a y value of 13. We're also asked for the value of our antiderivative at -5. So I'll jump over to -5, and there we see that our antiderivative value is about 12.5. Well, that winds up this video. For more calculus resources like these, see education.ti.com.